All right, welcome back for part 2 of 11.1. And just because I have to, I need to finish this. So we failed to reject the null. So we would say that there is not enough evidence to reject the claim of a uniform distribution. Sorry this had to get broken up into 2 videos. I didn't want to redo that whole video just for that end there though. All right, so again, what we're looking at here is a uniform distribution claims that these should all be the same. Clearly they're not. Our job is to say, are they far enough off from what uniform says they should be, the expected, to reject that claim of uniform, right? And it looks like these weren't. These were not far enough away to reject that claim. Let's try another one. Right? A doctor claims that the number of births by days of the week is uniformly distributed. To test this claim, you randomly select 700 births from a recent year and record the day of the week each takes place. At a significance level of 0.10, test the doctor's claim. All right. So the doctor is making a claim of a uniform distribution. So the doctor's claim is that the births on Monday should be the same as Tuesday, should be the same as Wednesday, and so on and so forth. So this table that we're looking at here, again, these are going to be observed. So we need to make another set of data over here that is going to be our expected. Now, if these were uniformly distributed and our K here is 7 because there's 7 days of the week, then each of these should be 1/7 of our sample size n. So that's our n up there. So each of these should be 700 times 1/7 or 100. So if these were perfectly uniform, 700 data points would give us 100 for every day of the week. Our job is now to compare the observed to the expected, to test, to see whether these, which are clearly not all 1/100s, right, to see if they're different enough from 100 to say that no, this isn't uniform, right? All right, so I've got a claim. My claim is going to lead to a pair of hypotheses. My null hypothesis is that my observed matches my expected, or that the observed distribution is uniform. If you want to write it out in words, my alternate hypothesis then is that the observed is not the expected, or the observed is not uniform. My data is the tables above, as well as an alpha level of 0.10. Right? All right, so to run the test, the first thing I've got to do is I've got to get these 2 data sets into my calculator. I'm going to put the observed in L1 and the expected in L2. Right? So stat, edit, I'll put the, I need to clear this old data out first. But I'm going to put that in there. I'm not going to make you watch that. I'll pause. I'll come back when it's all in. Okay, so I got it all, excuse me, I got it all typed in. I've got my observed, got my expected. Oh, I need degrees of freedom. What's going to be the degrees of freedom for this? Well, degrees of freedom is always k minus 1. So that's going to be 6 for our degrees of freedom. There are 7 classes. 1 less is our degrees of freedom. Right? So then stat, over to test, up to chi-squared goodness of fit, test. Observed is L1. Expected is L2. Whoops. Gosh, I hate when I do that. Okay. I don't know what I'm doing here. Let me try this again. Stat, test, chi-squared goodness of fit test, observed L1, expected L2, degrees of freedom 6, calculate my chi-squared test statistic, that's that 21.96 up there, my p-value, that's what I really want, is 0.001. Okay? I'm going to compare p to alpha. P is way less than alpha. When p is less than alpha, we reject the null hypothesis. What was our claim? Oh, our claim was a uniform distribution, so our claim was the null. So that means that there is enough evidence to reject the claim of a uniform distribution. Okay. Now, there's a lot of reasons why this could be occurring. I'm running the test tells me to reject. But if you think about it, some women, when they give birth, are going to choose to have the labor induced, and they might not choose to plan to have that labor induced, or maybe to have a C-section on a weekend day. They might push for a weekday. I bet if we reran this test and ignored Saturday and Sunday and just said it was uniformly distributed Monday through Friday, we would get that it was. We would have not enough evidence to reject that claim. But adding in the weekend, I think, is where it messes things up. And I say this as someone who was born on a Saturday. All right. Now, I noticed that we had two examples in this section, and both of them were examples of uniform distribution. So I grabbed this one and tossed it in here. It is not uniform. Unfortunately, it's not in your notes. So you'll just have to watch it here and see what you can get from it. All right, so here goes. All right, so a geneticist predicts that pea plants will grow in a 9:3:1 ratio of phenotypes. Now, depending on how much you know about biology, we can swap out some words here. We can remove predicts and call that our claim. Okay. The phenotypes are just the different types of the plants, like maybe green peas or yellow peas or wrinkled peas or smooth peas or whatever they are, the different phenotypes. So they're just the different ways that these things show up. And this right here, this 9:3:1 ratio, that tells me that there are 4 phenotypes, 4 different types of plants, and that for every, if I call them phenotype 1, phenotype 2, phenotype 3, and phenotype 4, that for every one of 4 that I see, I should see 3 3s, I should see 3 2s, and I should see 9 1s. And if I saw 2 of phenotype 4, I should get 6 3s, 6 2s, 18 1s. I'm just scaling it up. Okay? Now, the next part of this tells me that she observes a bunch of stuff. Now, I found it pretty easy in the last couple examples when I had a table, so I'm going to make one. So my phenotypes are 1, 2, 3, and 4. My observed is 160. Oh, wait, no. 160 is my N. So you observed 160 plants. 95 were this, right? Let's see. 28 were this. Let's see. 26 were phenotype 3 and 11 were phenotype 4. Okay. Now, I also know that when I did this, I put another column over here and call it the expected. Right? So I need to figure out what is the expected number of all of these. Well, here's where things get a little bit tricky, and I'm hoping you can follow me. For phenotype 1, I'm going to call that P1, we should see 9, let's see, 16ths of them be phenotype 1. For phenotype 2, it should be 3/16. For phenotype 3, it should also be 3/16. And for phenotype 4, it should be 1/16. Now I'm hoping you noticed that the numerators here are just the values for the ratios. Where did 16 come from? Well, if you add up all of those numbers, 9, 3, 3, 1, you get 16. So that means that there are 16 possible outcomes. 9 of the 16 should be phenotype 1, a probability of 9/16. 3 of the 16 should be phenotype 2, a probability of 3/16. So then the expected value, all of these numbers right here, the expected values for these guys should all be their probabilities multiplied by the sample size, in this case 160. And so for that first one, this is going to be 9/16 times 160, which is 90. The second one would be 3/16 times 160, which would be 30. This one would also be 30 because it's the same probability. And this would be 1/16 times 160, which would be 10. Now I'm going to check my math here by adding them up, because if those add up to 160, I should be right. So 90 plus 30 is 120. 120 plus 30 is 150, plus 10, 160, so we're looking good. All right? So what's my claim? Well, my claim is that the observed should be in ratio at 9, 3, 3, 1. My null hypothesis would be then that the observed is the expected, that they are in that proper ratio. My alternate would be that the observed does not match the expected, that they are not in that ratio. My data is the table above, and I just noticed something. When I copied this over, I didn't grab the significance level. So let's see if I can find it from the textbook where I stole this thing. Okay, and so the textbook level, significance level. Oh, we're supposed to be testing this at an alpha level of 0.05. So our data is going to have an alpha level of 0.05. Right? So I need to get this data into the calculator. So I'll pause the video and come back when that's done. All right, so I've got the data in. Oh, degrees of freedom. There's 4 categories. So our DF, our degrees of freedom, is going to be 3. There's always 1 less than K. K is the number of categories. So let's run this test. Stat, tests. I'm looking for the chi-squared goodness of fit test. Observed, I put in L1. Expected in L2. Degrees of freedom is 3. Okay. I calculate. If I needed the chi-squared test statistic, it's 1.04. But more importantly, I've got a p-value there. I've got a p-value of 0.79. When I compare p to alpha, p is much greater than alpha, so we fail to reject the null, or we would say that there is not enough evidence to reject the claim of, how do we want to word this? Our claim is that the pea plants are in ratio. The plants are in a 9:3:1 ratio. All right. That brings us to the end of section 11.1. I hope you have a great day. I'll see you back for the next video, the last video in 11.2.